Hello, everybody. My name is Murat Yuksel. I'm at the ECE department, and I am directing the Networking and Wireless Systems Lab. So a bit about me. I'm currently a professor at the ECE, affiliated with CS as well as CREO. Got my Ph.D. from RPI. My interests are in research, in general, networked, wireless, and computer systems. If I would like to summarize it in 3 words. But I would have in terms of recent focus, I have 2 main thrusts. I have wireless activity going on, specifically optical wireless and wireless systems, and more about network economics and network architectures, where I also look at some of the spectrum sharing, cloud networking, as well as the old traditional network economics and architectures problems. In terms of my teaching interests, I teach in computer systems and computer networking courses. I teach essentially senior level networks course, and I introduce 2 graduate level courses on network economics and architectures, as well as a course on software-defined networking. I am grateful that I have 8 PhD students right now. Pretty much all the work I do is enabled by them, and I have 1 bachelor's student right now in my group. I was fortunate enough to graduate 2 postdocs and 11 PhDs until this far. My collaborators are from various universities, as well as some industrial collaboration. Not a huge activity in industry collaboration these days, but I did have that earlier. My most funding is coming from NSF, and I do have an active funded project currently from NIST. I earlier had funding from other agencies as well. I'm not going to focus too much on the network economics and architecture side for this limited time. I will list it depending on how much time I have at the end, but I'm going to mostly try to summarize and a bit dive deeper on the wireless work I'm doing. You may have seen, if you have looked at wireless communications and networking before, you may have seen trade-off figures, tens of different ones. I actually like this triangle one, which means that you can only get 2 of the 3 things. Among the 3 main metrics that we all strive for in wireless systems is mobility, rate, and range. Essentially, what we most of the time end up doing is that start with 2 and then try to get the other one. If you look at, a bit history about this is that most of the 3G and 4G designs focused on low frequency range, which means that the signals were able to handle mobility as well as long ranges. And then they tried to increase the rate, which meant having more modulation schemes. And more recently, because of the exponential increase literally exponential increase in the wireless demand, everybody is now trying to strive for reaching the top of the triangle, which is the rate. More recent designs in 5G has been looking at rate and range come together, which means that higher frequencies, things like, for example, millimeter wave, and then they try to increase mobility. My focus is pretty much on the other side of the triangle, where I focus on utilizing directional signals, try to increase spatial reuse by having extreme directionality, and use software techniques to essentially enable mobility. I'd like to remind you about the electromagnetic spectrum. Essentially, what we have been doing in wireless is mostly within the cellular band, which is essentially below 6 gigahertz. As you can see, when in the whole spectrum, this is a very limited amount of band. So we are trying to essentially go into these higher frequencies. And FSO, optical wireless, as well as millimeter waves, these are very large bands. Most of my work has been in the FSO area, free space optical, or another word for it is optical wireless area. The nice thing about these bands is that they are unlicensed, so you don't have to fight for getting a band go through FCC and all. You can achieve quite a lot of high rates, as I mentioned earlier. Because of the highly directional antenna designs, you can achieve quite a bit of spatial reuse, which means that you can have multiple communication links at the same time without interfering each other. But the problem with these is that range, because of the wavelength being so small, you can't really go far, and mobility, which has been the key focus of my work. So essentially, what I do is I design modules, optical wireless, as well as other high frequency communication modules that focus on putting together multiple elements, multiple transceivers, multiple transmitters or receivers, and then use these short range links opportunistically and use software control to handle mobility issues. A bit of background in FSO communications. Essentially, you can think about it as pretty much fiber optic communication without the fiber. So we have got a transmitter, which is typically a laser or an LED. And then on the other side, you have a photodiode. We literally just turn on and off the light. And you know, on the receiving end, we just try to decipher what was sent. These components, these optical wireless or optoelectronic components, can be quite low cost. I mean, they may be quite expensive too. Of course, if you want to go really, really long ranges, of course, these lasers can be quite expensive. But particularly with LEDs, they are pretty cheap and amenable to mass integration. You can actually put many of them in a small, dense, you know, you can put many of them in a small area. So my work has been sort of like looking at it, why not use many of these components and try to achieve handle mobility. But I call this as essentially software-defined mobile FSO, where we consider spherical surfaces, like pretty much like a ball. You can think about it as a tennis ball or maybe a soccer ball, and cover these balls with transceivers, LED, and you know, photodetector combinations. Essentially, the idea is very simple. If these two nodes move with respect to each other, there will still be another transceiver on them that will be in alignment, most likely in alignment with each other, which is essentially a key problem with these highly directional wireless signals. If you lose line of sight, or if you essentially just misalign the transmitter and the receiver, then you lose the link. We designed actually these modules and integrated them with software protocols that can handle autonomous detection of which transceiver is currently aligned with the neighbor. And we essentially did multiple projects on these concepts. And some of the prototypes, as you can see, the one that you're seeing on the left bottom is pretty much like a soccer ball size. These transceivers we developed ourselves were composed of infrared LEDs and a photodetector. They are roughly about 2.5 centimeters in diameter. So, I mean, of course, I can go on and on there, but let's step back a little bit. Where are we going in the larger scheme of things? Currently in the 3D space, if you look at the wireless networking, in order to provide communication, right now, what we are considering, what the community is considering is UAVs. Providing communication by using UAVs is going to look like this, where you're going to have, if you're not going to use any higher frequencies, if you're just going to stick with sub-6 gigahertz frequencies, then there will be a lot of interference. So what should be actually is this, rather than having these high altitude components talking to each other with wireless, with regular legacy wireless frequencies, we should use directional, very directional links. So this is another essentially context where I have projects and work on. So the challenge here is, of course, that these links, these directional links now need to be line of sight capable. They need to be able to handle you know, mobility. So we looked at and prototyped some of the challenges there was to discover and maintain these line of sight and directional links. So we had drones essentially that are searching for each other by doing mechanical steering of the FSO transceivers. So we were able to show that these drones can discover each other below, actually in sub-second, which is quite a bit of achievement. For the time sake, I'm just going to mention briefly about some of the other projects. In the optical wireless space, I do have significant work going on in visible light communications. Again, very similar concepts. Rather than using one big bulb to illuminate the room and provide wireless access, we are using focused, spotted LED lights, but try to handle illumination as well as communication efficiency at the same time. So where do I want to go with all this? Well, I'd like to cover mobile gadgets with optical wireless receivers, and that's one of the things I'm currently working on and publishing on. I'm imagining a world where we cover our smartphones with photodiodes and have light receivers on them. And I'm also currently also looking at air-water optical wireless communication, where you don't have to worry about buoys on the surface of the water. Underwater communication is actually quite a bit of a challenge. So right now I'm trying to use optical wireless there. In terms of the extension of the soccer balls, I'd like to miniaturize them. I'd like to make them look like a lollipop, so that they can be ubiquitously deployed in various contexts. In terms of opportunities, anything related to RF challenge settings like hospitals, aircrafts, my work would be very much relevant there. I am very much interested in smart city applications, as well as large testbed developments where you could do live lab experimentation. I'd like to also mention one of the recent grants we just got with Azadeh and Dr. Gong on essentially, again, similar concepts. We are trying to do directional software-defined radio for indoor as well as outdoor, but very crowded, very dense settings, providing essentially gigabit per second communication link, as well as hundreds of megabits per second communication links in outdoor settings. I do have significant activity going on in regular networking solutions for wireless, where I'm just going to list them here without going too much details in it. Essentially, I have some device-to-device networking research going on. The first one is actually funded by NSF, and the second one is funded by NIST. We are looking at D2D routing and SDN integration issues in these contexts. The fundamental question in these projects is, if the infrastructure, wireless infrastructure fails, what can we do by using our devices? And finally, I'm just listing the network economics and architectures projects that are currently active. So we have one active NSF project right now with RPI that is looking at internet exchange point economics. How can we make ISPs more peer with each other more effectively? Another project that I'm very excited and actively involved in is internet-inspired integration of EVs to power grid. We are essentially applying internet congestion control techniques on EV charging control, which resulted in actually very interesting papers. I'm more of a supportive role on that. And we wrapped up recently a spectrum sharing project, which involved multiple universities, as well as public administration department at UCF. I'm going to just wrap it up here, just a